Okay, we're back again. This time we're going to look at homework set 24. This is the homework that is due Wednesday of this week. Um, the first problem, problem 20, is just a basic collision problem. Now you're going to have several of these on the exam next Tuesday. This is just the standard, what do you do when two things collide? And in this problem, we have two blocks. We have a 4 kilogram block that's moving at 12 meters per second to the right. And we have a 6 kilogram block that's also moving at 12 meters per second, but to the left. And so this is the before the collision. After the collision, we're told that the 4 kilogram block rebounds back at 3 meters per second. And what we don't know is, what is this 6 kilogram block doing? Is it moving left? Is it moving to the right? How fast is it going? This is a collision, and for every collision problem, we start here. P initial is equal to P final. And two things I want to point out. That this is only true for the system comprised of everything that interacts, everything that hits. In this case, both blocks. And the second thing I want to point out is that this is a vector equation. And this is conserved as a vector. And so we need a coordinate system with all momentum problems. Let's call to the right positive and to the left negative. Now, before the collision, I have 4 kilograms moving at 12 meters per second, and it's moving to the right, so that's positive momentum. I also have a 6 kilogram block moving at 12 meters per second, and that's to the left, so that's negative. And then the collision happens. That equal sign represents the collision. I'll remind you from last day, in this equation, initial means right before the collision, and final means right after the collision. Okay? No dilly-dallying around. So after the collision, we have 4 kilograms moving at 3 meters per second, and it's moving left, so that's negative momentum. And then I have this 6 kilogram block, and I don't know whether it's moving left or right. So I just assume that it's moving to the right. I give it a positive variable, and then I solve for that variable. If I get a negative answer, then I know I guessed wrong. Okay, so my goal is to solve for this final velocity there. So this is going to give me 48 franci minus 72 franci is going to equal negative 12 franci plus 6 kilograms V final. Well, if I take the negative 12 over to the other side, okay, I'm sorry, I'm gonna have to kill my phone. Okay, so what I get here is, let's see, I get negative 24 franci is equal to negative 12 franci plus 6 kilograms V final. And if I bring the negative 12 over, it becomes positive 12. Positive 12 plus negative 24 is a negative 12. equal to 6 kilograms V final. And this gives me a V final is equal to negative 12 over 6 kilograms. That's going to be negative 2 meters per second, or 2 meters per second left. Okay? So I can either write my answer as negative 2 meters per second, or I can say it's 2 meters per second left. The 2 meters per second is the magnitude, the size, how fast it's going, what you would see on the speedometer. The direction is either the minus sign or the word left, but you can't use both, because negative left is to the right. Okay, now we've seen several examples of this type of collision. You should be able to solve these types of collision very quickly. Okay, let's look at a couple of pendulum problems. If we look at problem 31, in that problem, we have a pendulum that is length 4 meters, and we swing it up so that, oh, that got bigger, didn't it? So that its center of the bob went up a distance of 0.8 meters. And we find that when it swings down here, we're told that it strikes this block That block is on this floor. Now, the mass of this bob is 3 kilograms. The mass of this block is 1 kilogram. And we're also told in the problem that the speed of the block after the collision is measured to be 6 meters per second. So after the collision, this would be before, and this would be after. Okay, the first part of this problem wants to know the speed of the ball right when it gets here. Those are the international symbol for speed. And the collision hasn't happened yet. So this is not yet a momentum problem. It will be a momentum problem when we hit the block, but right now it's just energy transfer. It was potential energy, it's going to be kinetic energy. So we start in part A with the grand high energy Werk equation, which is where we always start with energy problems. And we note that a string, a Tarzan swing, does no Werk, because it's always pulling in one direction, and you're always moving in a direction that's perpendicular to that, okay? So a string that you're swinging on does no Werk. Now initially, that block is up off what we're calling the floor, and so I have gravitational potential energy, but it's not moving, and there's no springs, so that's just silly talk. And so this is all of the energy that it starts with. At the end, when it's about to hit the block, it's moving, so it has kinetic energy, but no gravitational energy, because now it's at its lowest point. So I can see that the mass is going to cancel out here, and I can solve for V final squared is going to be equal to GH initial over, I'm multiplying by 2 GHI. Okay, and that means that the V final is just going to be the square root of this. Well, that's going to be the square root of 2 times 10, we'll call that meters per second squared, and h is 0.8 meters. Okay, and so this is going to be the square root of 16 meters squared over second squared. Well, the square root of 16 is 4, and the square root of meters squared is meters, and the square root of 1 over second squared is 1 over second. So I get 4 meters per second. Now, that's how fast it's going, and I put a positive because it's going to the right. I'm going to call to the right the positive x direction. Now, we're asked the speed of the ball immediately after the collision. Well, now it's a collision problem, so I start here. Right before the collision, the only thing moving is the ball, and it's got a mass of 3 kilograms and a speed of 4 meters per second. And it's going to the right, so that's positive momentum. I could also put 1 kilogram for the block times 0 velocity, but that's just wasting ink. After the collision, I've got the 3 kilogram block moving at some speed that I don't know, so I assign it a positive variable. And then I have this 1 kilogram block moving at 6 meters per second. And I put a plus sign there because it's moving to the right. So that means that a positive 12 franci is equal to 3 kilograms V final plus 6 franci. So if I subtract 6 from both sides, I get 6 franci is equal to 3 kilograms V final. And that's going to give me an answer of V final is equal to 2 meters per second. Or I could say 2 meters per second to the right. I could either say a positive 2 meters per second or 2 meters per second to the right. If you're asked for the magnitude and the direction, you would need to do one of those two. Now, we're asked in part C what flavor of collision we have here, an elastic, an inelastic, or maximally inelastic. Well, I know for a maximally inelastic, they stick together. That's the definition of a maximally inelastic collision. And that's the collision where they lose the most energy allowed by law. And here, they didn't stick together. I know that because this block is moving at 6 meters per second, and this ball is moving to the right at 2 meters per second. If they were stuck together, they'd be moving the same velocity. Okay? So that means it's got to be either elastic or inelastic. Well, for elastic, I know that my mechanical energy before is equal to my mechanical energy after, and in this case, mechanical energy means kinetic energy, where for inelastic, we lose some of that energy that we start with. So what I need to do, I can't just look at this situation and sniff the air and say, oh, that just smells like an elastic collision. You can't recognize an elastic collision without doing a calculation. my initial kinetic energy is 1/2 times the 3 kilograms of the ball times its speed of 4 meters per second squared. So that's going to be 24 joules. Afterwards, I have the 3 kilogram block moving at 2 meters per second. I got to square that. Plus I have the 1 kilogram block moving at 6 meters per second. And I've got to square that. So this is going to be 6 joules plus, that's 36 times a half would be 18 joules. And lo and behold, when I add that together, I get 24 joules. And since it started with 24 joules and it ended with 24 joules, this is one of those once in a blue moon situations where it was totally elastic. And that's just really hard to create in real life, but on paper we can always create anything. Okay? So that's the second problem in this homework assignment. Let's go and look at the last problem. The last problem is problem 32. Okay, and got to turn the page for that one. This one has everything going to the left. Okay, this time we've got a block. It's sitting in front of a rough patch with a coefficient of kinetic friction equal to 0.2. And this block has a mass of 6 kilograms. And there's a bob of a pendulum, and this pendulum started up a distance h. Okay. So let me just, I'll do it to the bottom of the bob here. And the first question we have is, how big is h? Well, we're told in the problem that this is a 4 kilogram block, ball. That turns out not to be so important. We'll see that cancels out. What is important is that right before it hits the block, it's going at 5 meters per second. And so if we use the energy equation, again, noting that a pendulum, as it swings down, the force is always going to be a tension force up the string, and the motion is always going to be perpendicular to the string. So that does no vec. So again, we start with gravitational energy and we end with kinetic energy. As I promised, the mass cancels. And in this case, we're looking for the initial height. And so that initial height is going to be v final squared over 2g. That's going to be 5 meters per second squared over 2 times 10 meters per second squared. And when I solve that, I get 25 over 20, or 1.25 meters. Okay, so this was 1.25 meters. Now in part B, we want to find the velocity of the bob right after the collision. And we're told that after the collision, this guy here, the block, is moving at 3 meters per second. And we want to know, what's that bob doing? Well, this is going to be a collision, so I'm going to use initial momentum is equal to final momentum. Now in this case, a lot of stuff is going to the left, so I'm going to choose to the left to be my positive x direction and to the right to be my negative x direction. I get to choose every time I start a problem. And so before the collision, I only have the 4 kilograms moving at 5 meters per second, and it's moving to the left. I'm calling that the positive direction, so that's positive momentum. The block is not moving yet. Now, after the collision, I've got that 6 kilogram block moving at 3 meters per second, and I have that 4 kilogram bob moving at some unknown velocity, so I'll make that a positive variable. Well, that tells me that 20 franci is equal to 18 franci plus 4 kilograms V final. Now that's just algebra. If I subtract 18 from both sides, I get 2 franci on the left. I divide by 4 and I get a final velocity for the bob of 1/2 meters per second. And it turned out to be a positive 1/2, okay? So I would write that as positive 1/2 meters per second, or 1/2 meter per second left. Because in this problem, positive means left. Now, we want the kinetic energy just before the collision. This is part C. Well, before the collision, the only thing moving is the 4 kilogram bob, and it's moving at 5 meters per second, and that's going to give me 50 joules. Part D asks me to find the kinetic energy after the collision, and by after I mean right after. I can't wait for that block to slide across the rough floor and stop. So that means I'm going to have the 4 kilogram block moving at 1/2 meter per second, and I'm going to have the 6 kilogram block. This was a bob, not a block. This is going to be 3 meters per second. And when I multiply that all out, I get 27.5 joules. Now we're asked what kind of a collision this is. Well, I know they don't stick. Spell it right. Therefore, max inelastic is out. And I also know that the kinetic energy initial is not equal to the kinetic energy final. So that means elastic is out. And so the only thing left is inelastic. Remember, there's only the 3 flavors. Okay. Now, the last part of this problem asks us if this block starts out moving at 3 meters per second across this rough surface, how far will it travel before it stops? Well, remember how you decide whether to use energy or momentum. First you ask, is it a collision? If it's a collision, it's always momentum, and momentum's conserved. The second question you ask yourself is time involved? If time's involved, it has to be momentum. It can't be energy. Energy will never tell you anything about time. Well, in this case, it's not a collision and it's not about time. And so in those cases, it's an energy problem. So if I look at part F here, I start with energy initial plus Verk external is equal to energy final. Now, because this block is on the floor, there's no gravitational energy. Because there's no springs in the problem, there's no spring energy. So by energy, we mean kinetic energy. So this would be 1/2 mv initial squared. The Verk done is going to be the Verk done by friction, and because it's moving to the left and friction is acting to the right, that's going to be negative Verk, the kinetic friction by the floor on the block times the distance. And when it grinds to a halt, it will have no kinetic energy left. So if I plug in, I get 1/2 times 6 kilograms times 3 meters per second squared minus this friction force, delta x, is equal to 0. So if I knew that friction force, I could solve for the distance. Well, anytime I'm looking for a force, I draw a free body diagram. The weight force on that block is going to be 60 newtons. The normal force by the floor on the block is also going to be 60 newtons because there's no acceleration up or down. This kinetic friction is the easy kind of kinetic friction. That's just the mu sub k times the normal force. In this case, that's going to be 0.2 times 60 newtons, and that's going to equal 12 newtons. So I can come back here and I can plug in for the friction force 12 newtons. And now I'm ready to solve for delta x. Okay, this is going to be 18 joules minus 12 newtons delta x, spelled with a delta, is equal to 0. If I bring that over to the other side, it becomes positive, and we get delta x is equal to 18 joules divided by 12 newtons, and that's going to be 1.5 meters. And that's the wrong answer. And the reason it's the wrong answer, you should have caught me on this. This is not 18, but 27 joules. And so that's going to make this 27 joules. And that's going to make this 2 1/4 meters. Okay, so that's one error. If I make 2 more errors, you get a rebate on your tuition. It's easy as that. Okay, thanks. This has been another chance to practice homework with homework number 24. Have a good day, folks. We're going to stop.